In this class, we will discuss about some of the properties of fluids in detail and related problems. So, surface tension, compressibility, and capillarity. So, these three things we will discuss now. Actually, here you know in terms of fluids that solids possess a property called bulk modulus of elasticity, which is given by the ratio of direct stress to volumetric strain. Similarly, in the case of liquids or fluids, we can define the bulk modulus of elasticity as the ratio of change in pressure. So, this is change in pressure to the volumetric strain. So, volumetric strain is nothing but the ratio of change in volume to initial volume, that is dV by V or delta V by V. And change in pressure, when a body is subjected to some pressure or a fluid mass is subjected to some pressure, as you know, as the pressure increases, volume reduces. So, this volume gets reduced. So, that change in volume divided by the initial volume along with the change in pressure. So, initial pressure difference final pressure, it bears a ratio called the bulk modulus of elasticity, and the units, as you know, this pressure will be in Newton per mm square or Newton per meter square or pascals. This ratio, volumetric sphere, of course, they don't have any units. So, if this change in pressure is in Newton per mm square, K also will be in Newton per mm square. So, this compressibility is an inverse measure of elasticity. So, it is an inverse measure. So, elasticity is defined as that in terms of K, whereas compressibility is reciprocal of K, 1 by K. So, units of compressibility will be now millimeter square per Newton. So, in the case of gases, this compressibility effect is very high. So, that is why gases are treated as compressible fluids, whereas in the case of liquids, this compressibility effect is low and they are called as incompressible fluids. So, liquids are treated as incompressible and gases are treated as compressible. That means the effect of the pressure on the volume is enormous in the case of liquids, whereas it is negligible in the case of it is enormous in the case of gases, whereas it is negligible in the case of liquids. Now, coming to the surface tension part, I already explained this in the first video. It is the tension created on the free surface of the fluid. So, it is expressed as the force per length, unit length. So, that surface tension we can always have in practical examples also. We will have three examples here. One is the liquid droplet. So, when a droplet of a liquid falls, what happens here? There will be a pressure difference between the inside liquid droplet and the outside pressure. So, that pressure difference we can take it as P, and along the circumference the surface tension force will be developed to keep the droplet in equilibrium. We can observe here that the pressure acts inside, inwards, whereas the surface tension force acts outwards. So, this pressure force should be equated to surface tension force for equilibrium of the droplet. So, if you equate them, if you convert this surface tension to surface tension force, so this surface tension sigma will be acting over the circumference, which is nothing but pi d by d is the diameter of the droplet, and that force will be equal to this pressure intensity multiplied by the area. So, cross sectional, because pressure always acts over an area, pi d square by 4 is the area. So, if you equate these two, so this is, you can see that this is an outside pressure, this is an inside pressure, they should be equated. So, if we equate them, we are going to get the pressure difference expression as P is equal to 4 sigma by D. So, when you are using this formula, you should be careful about the SI units. So, sigma will be in Newton per meter, P will be in Newton per meter square, and D will be in meters. So, they are the SI units, even though if they are given in different units, you have to convert them to these units. This is in the case of a liquid droplet, P is equal to 4 sigma by D. This formula you have to remember to solve the problem. In the case of a soap bubble, second example, so you can see an apparent layer also formed along the circumference. That means you can observe two circumference layers. So, therefore, here when you are taking the circumference, the surface tension force, this surface tension force will be acting over two circumferential layers. So it instead of pi d it becomes 2 pi d, and that should be equated to the inside pressure. That inside pressure will be P into pi d square by 4 as usual. So in this case P becomes 8 sigma by d. So see the difference here. So in this case the pressure will be almost double that of the pressure what is there in the liquid droplet. Now coming to the liquid jet. So when a jet of a liquid emerges out, so then also you will be having a surface tension force which will be acting along the length of the jet. So this is the jet. So if you take L as the length of the jet, along the length surface tension force will be acting outwards, whereas the pressure will be acting inwards. If D is the diameter of the jet, so then what happens here? So this surface tension sigma will be acting over two lengths, L plus L, 2L, and it should be equated to the pressure which is acting over the, what we can say, D into L means that is the diameter multiplied by this length. So D into L it will be acting. So in that case you will be having the expression for a liquid jet. In the case of a liquid jet, the pressure intensity, the difference in the pressure intensity is given by 2 sigma by D. So if you simplify that, you can observe that you will get P is equal to 2 sigma by D. So that means in this like this we can have for three different cases you can always find out the surface tension force or the intensity of pressure, the difference in the pressure between the inside and outside of the liquid droplet or a soap bubble or a liquid jet. So these are the expressions directly you can use to find the pressure difference or the surface tension if you know the pressure difference. Now the third important property is the capillarity. So capillarity is can explore only in the case of liquids or fluids where suppose if you immerse a thin tube in a container which contains some liquid, you can observe that the liquid enters the tube and stands somewhere in the tube, somewhere at some height in the tube. Maybe it may be at a higher level than of above with respect to the free surface outside the tube, or it can be at a lower level also. If it is at the higher level, then it is called as capillary rise. If it is at lower level, it is called as capillary fall or depression. Now in this case, H is the capillary rise here. Okay, so this liquid, normally in the case of water, it will be like this. So it stands somewhere here in the tube. So a surface tension for sigma will be acting like this. It will be acting like this, which makes an angle some theta with respect to the tube, surface of the tube. The theta is called as the angle of contact. Liquid specific gravity, if you specific weight of the liquid, if you take it as gamma, and D is the diameter of the tube, small tube, so then you can derive an expression for this capillary rise or capillary fall H. So to derive the expression, what we have to do is, we have to equate the weight of the liquid column which is there above this surface in the tube to the component of surface tension in the opposite direction. It acts in the opposite direction. You can see here sigma is acting like this, making an angle theta. Its component along the vertical direction will be like this. So this is the component vertical direction, this is the component in the horizontal direction. And this sigma will be acting over the circumference. You can see here. So it acts over the circumference. So if you want to convert that force, surface tension into surface tension force, the sigma cos theta, whatever is acting, it is acting over a length of the circumference, that is pi into d. So sigma cos theta into pi into d is the surface tension force which is acting in the opposite direction of the weight. So weight will be acting like this. So this should be equated to this. This is downwards, this is upwards. So if you want the weight of this liquid column which is there in the tube above the free surface, this weight is given by the specific weight into volume. So because specific weight is defined as weight divided by volume, weight is given by specific weight into volume. So specific weight into volume of that liquid column will be area multiplied by the height. So area is in diameter is d, area of the tube is pi d square by 4 into height is h. So this becomes the volume. So this is equal to sigma cos theta into pi d. Now if you simplify this, you get h as 4 sigma cos theta divided by gamma into d. Please note that here H is the capillary rise in meters. We are talking about SI units, and sigma is the surface tension force of that particular liquid which is in contact with some other liquid, and which is expressed in Newton per meter, and gamma is the specific weight of that particular liquid which is expressed in Newton per meter cube. D is the diameter of the tube, capillary tube, which is expressed in meters. So normally the value of theta for water it is almost 0 degrees, and for mercury it is almost 130 degrees. Okay, so depending on the type of the fluid or the liquid, the value of theta varies. So now these are the three important properties. One is compressibility, second one is surface tension, third one is capillarity. So I have given the expressions for those things. Now we will take up one problem about that capillarity problem. So here what they have given here is they have given the value of surface tension of water with respect to air. Of course, that's 0.075 Newton per meter, and surface tension of mercury he has given 0.52 Newton per meter. Theta of water 0 degree, theta of mercury 130 degree. Diameter of this small tube is 3 mm. So it is diameter will be very small. It is a very thin tube. So this process you can observe in roots of plants, where through those capillary tubes which are present in the roots, water will be taken for the plant growth. Now I want to find the value of capillary rise or capillary fall, whatever it is there for this data. So the solution runs like this. So I am going to use this formula directly. First of all, I will take that the liquid is water. HW I want to calculate. Liquid is water there. 4 sigma W cos theta W by gamma W into D. So 4 into sigma W has given 0.075 Newton per meter. It is in SI units, no need to convert. Into cos theta, theta W has given 0 degree. Gamma W you should know 9810 Newton per meter cube. Even if they don't give, you should know this, you have to substitute into diameter of the tube is 3 mm, convert it into meters, 3 into 10 power minus 3 meter. So everything, so this is in Newton per meter, this is in Newton per meter cube, this is in meter. So if you simplify that, you are going to get the answer in terms of meter only. Later on multiply that by 1000, you will get in millimeters. You are seeing that since cos 0 is 1, you are going to get positive value here, plus 10.2 mm. Because normally finally it is expressed in millimeters, I am going to write it as 10.2 millimeters. Since it is positive, it is capillary rise. Normally for water, it will be capillary rise. That means the liquid water level will rise above the free surface. Now coming to the mercury, suppose if instead of water mercury is used, the value of theta is different, sigma is different, gamma is also different. 4 sigma Hg cos theta Hg divided by gamma Hg into D. Here diameter and this 4, only those two are same, others are different. 4 into for mercury surface tension is 0.52 Newton per meter into cos theta Hg is 130 degree divided by gamma Hg is nothing but specific, this is specific gravity of mercury, so which is 13.6, you have to remember that, into specific gravity of water. So when we multiply the specific gravity of a fluid by specific gravity of a fluid by specific weight of water, you are going to get the specific weight of that particular fluid. So gamma Hg will be 13.6 into 9810 into diameter. Of course, it is same. It is in meters. So 3 into 10 power minus 6 because it is 3 mm. If you simplify that, you are going to get negative value because cos 130 is negative. Cos 130 is negative. So negative value you are going to get minus 3.34 into 10 power minus 3 meter, or if you convert it to millimeters, minus 3.34 millimeter. Since it is minus, it represents that it is capillary fall. That means this mercury level it will come below this free surface. Then this becomes your H. So if H is negative, the meaning of that is in the tube the level of that liquid is below the free surface which is outside the tube. So this is how we can compute the capillary rise or capillary fall for a given liquid. Only thing you should know the surface tension value and the angle of contact theta value and the specific weight of that particular liquid.